All right, thank you, Ryan. Thank you to all of the organizers for the invitation to speak and also for the hard work in organizing this conference. I know it's a lot of work and there's a lot of people from a lot of different time zones, so there's a lot of coordination involved. But I just want to publicly acknowledge all of the organizers for that work. So yeah, so I'm going to be talking about quantum walks, and I'm going to approach this from the perspective or the philosophy that less is more. So instead of trying to cover all the amazing applications of quantum walks and the whole scope of research that's been done on this field over the past couple of decades, I'm going to be just focusing on a single problem, so that way you can take away something very concrete. So I kind of want you to have a firm understanding of one thing rather than a very surface level understanding of perhaps the whole field. And so I'm actually going to be presenting this as if I'm teaching a class. So I'm actually going to be writing everything out as if I'm lecturing. And so, so I encourage you to treat this like a class. So feel free to ask questions as we go. I have the window with your questions open, so I'll be able to look at them. And so feel free to ask questions as we go, or to ask for clarifications of things that I write down, and certainly to point out any mistakes if I make any typos and things like that, just like you would in a normal class. And so this is our tutorial on quantum walks. And I want to focus on one specific problem, again, so that you have a concrete understanding of what's going on. And this is called the spatial search problem. And the idea here is that you have some type of database or network or something like that. So let me just make up a network real quick. So you have some vertices and nodes, something like that. And the idea is that there's a certain item, a certain vertex that you're searching for. And so there's different approaches to trying to find a particular vertex. We call it a marked vertex. So we're trying to find a marked vertex. And one way to do this is using a random walk. And so there's a question about what the necessary mathematical background will be for this. You can do all this using linear algebra rigorously, using all the math that can be involved with quantum computing, but I'm actually not going to use any linear algebra at all. And so the idea is for this to be accessible and understandable to people who are in like high school even. And so, so if you want to solve this with a random walk, what you can do is you can start at a random vertex. So let's say we start at this vertex here and we ask, is this the vertex we're looking for? If it is, great, we're done. If not, what we'll do is we'll jump to one of the 4 neighbors at random. So maybe at random, we'll jump over here to this vertex. And now we ask, is that the vertex we're looking for? If yes, we're done. If no, we'll jump randomly again. Now there's 3 different directions we can jump at random. Let's say we jump down here and we ask, is that the vertex we're looking for? If no, we'll jump randomly again. Now there's 4 directions. Maybe we'll jump back here. We'll jump, and basically we'll keep jumping around at random on this network or database or graph of vertices and edges until we end up, let's say here, and we go, is this the marked vertex we're looking for? Yes. And now we have found our marked vertex. So this is one approach to doing this search problem. And it's called spatial search because there's some spatial arrangement to the vertices where you can't jump from one vertex to any other. Like you can only jump to nearest neighbors. And so let me just write that down. So one approach is to use a random walk. And there'll be some expected runtime. So some number of steps that it takes in order to find the marked vertex. And it'll be different depending on what network that you have, how big it is, and so forth. And a very reasonable algorithmic question is to ask, how long does it take a classical random walk? And then extending that to the quantum realm, how many steps would it take for the quantum version of a random walk, which we call a quantum walk? And so this will be letter A in this outline. You'll notice I lecture in an outline. And so this is letter A under that. So our question is, how does a classical random walk compare to a quantum random walk? And the hope is that a quantum walk will be faster than a classical random walk, so we get an algorithmic speed up. All right, I don't see any more questions. So let's continue on to letter B, still under the spatial search problem. So again, how long a classical random walk and how long a quantum walk takes to search a graph will depend on the graph. And so we're going to focus on just one particular graph that is very easy to work through in our roughly 50 minutes that we have today. So this tutorial, we're going to focus on the complete graph or the all-to-all network. So the complete graph or all-to-all network is a graph where every vertex is adjacent to every other vertex. So every vertex is directly connected to every other one. So let's say we have 4 vertices, just so I'm not drawing a billion vertices. So for the complete graph, every vertex is connected to every other. So 1 is connected to 2, 3, and 4. 2 is connected to 1, 3, and 4. 3 is connected to 1, 2, and 4, and 4 is connected to the rest. So this is a complete graph with 4 vertices. So I'll let capital N denote the number of vertices as is customary in the field. So here this is 4 vertices, but we could have 10 vertices and they're all connected to every other one and so forth. To answer a couple of questions, one question was, are walks allowed to revisit nodes? Yes. I mean, if you're jumping around at random, even on this network, you could jump back to a node that you've already visited before. So that's allowable. And then there was another question, which was, can we transition between classical and quantum walks in the same system? I mean, if you do a quantum walk and you measure it with every step, which is typically what you don't want to do, right? Typically with a quantum computer, you want to let it evolve quantumly and you only measure at the end. So if you were to measure a quantum walk at every step, it would actually be the same thing as the classical walk. So in some sense, there is a close relationship between the two, but you generally don't want to measure partway and then collapse your system. And then you want the quantum walk to evolve in a superposition, and we'll get to that more in a little bit. So yeah. And also, if I answer a question inadequately, or or later on it kind of spurs more thoughts, then feel free to follow up and just try to ask again or ask in a different way. Thank you for those questions so far. Okay, so we're going to look at the complete graph or all-to-all network. And there's a few reasons for this. One is that this is a very simple graph to look at. It's actually easy enough to analyze that you can exactly find the way that a classical random walk and a quantum walk evolve on the complete graph. Whereas if you have a really complicated network like this one, especially if it's very big, then it's much harder to find the exact evolution. But with this thing, there's so much symmetry that it's exactly solvable. So that's one reason why we're looking at this. A second reason why we're looking at this is that this complete graph is actually equivalent to the unstructured search problem of Grover's algorithm. So you know that for those who are more familiar with quantum computing, there's this famous algorithm called Grover's algorithm that searches an unordered or an unstructured database. And that is actually equivalent to the complete graph, meaning that you can go from checking any vertex to any other because they're directly connected. Whereas in something like this, that is not true. Like if you are at this vertex, you can only then check the 4 neighbors that it has. You can't jump from this vertex to this one over here. And so that answers another question that just appeared a minute ago, which is that, can you randomly jump to a non-connected vertex? And the answer is no. If you wanted to jump to a vertex that was over here, you would need an edge connecting them. So the idea is this process respects the locality of the system, because there may be some physical systems where things are physically apart and you can't just jump, long distances. So we insist that you can only jump from a node to one that it's connected to. All right, so this is the walk formulation of Grover's unstructured or unordered database. And so if you are familiar with Grover's algorithm, that's actually going to reveal to you what the runtime will be. So a classical random walk, as we'll see, will search this in order n, where n is the number of vertices, whereas a quantum walk will search this in order square root of n, which is the same as Grover's algorithm. So we get that quadratic speed up. So this is like the quantum walk version of Grover's algorithm. Another thing that I want to point out is we're focusing on this because it's great for pedagogical reasons. And I actually wrote a paper recently that's on the archive at the moment, where I explore search on this complete graph and for arbitrary n very thoroughly. And so we only have so much time to discuss it today, but there's a lot more details and all the math is worked out in this paper. So the paper is called Unstructured Search by Random and Quantum Walk. Unstructured search, again, referring to the complete graph. Oops, I'm missing an R there. That's what happens when I talk and write at the same time. Unstructured search by random and quantum walk. So I explore both the classical random walk and also the quantum walk. And that's on the archive. You can just Google that title and it should come up. And finally, one more thing before we look at this is that there's actually different types of quantum walks. And in this paper, I actually talk about 2 different ones. We're only going to focus on one in this tutorial. We're going to focus on the discrete time quantum walk. And the discrete time, well, I guess walks, random walks and quantum walks. So, okay, there's no more questions. So let's go ahead and look at how a classical random walk searches the complete graph of n vertices. Okay, so let's put this in Roman numeral 2. So this is a random walk, which is implied to be classical. So maybe I'll put classical in parentheses. So this is a classical random walk or just a random walk. And let's go through the search algorithm together. And again, I'm not going to use any linear algebra or anything like that, although you can formulate this in terms of linear algebra, and to do all the math proofs of everything, you would actually do that. So let's work through a concrete example together. Let's go ahead and use this graph with 4 vertices. That way, we're not drawing like 1,000 nodes or something like that. So again, we'll just look specifically at the case where there's 4 vertices. And let me draw that. So you have vertex 1, 2, 3, 4. Everything's adjacent to everything else. And let's say the marked vertex is vertex 2. So I'm going to say 2 is the vertex that we're looking for. But of course, we don't know that yet. We're trying to find that. But just make it concrete. So what that means is that we would start at a random node, let's say vertex 1, and we ask, is this the vertex we're looking for? We find out, no, it's not. So you would do this by like querying some like Oracle or something like that. So if not, what we do is we jump at random to one of its adjacent vertices. So maybe we jump randomly to vertex 3 and we ask, is this the vertex we're looking for? No, jump at random. Now we're at vertex 2. We ask, is this the vertex we're looking for? Yes. And so now we would stay here. So because once we find the marked vertex, there's no reason to jump randomly away from it. We want to stay there. So as a graph, this search problem ends up looking like the following. So if you're at vertex 1, 3, or 4, you can jump wherever you want. But if you're at vertex 2, you can only stay there. So what we do here is we put a self loop at vertex 2, and then you can only jump to vertex 2. You can't jump away from it. So this would be what it means to be a marked vertex as a graph, as a random walk. So again, if you're at vertex 1, you could jump to 4 or 3 or 2, but once you jump to 2, you could only jump in place and stay there. So vertex 2 acts as an absorbing vertex, meaning like once you jump there, you're stuck. So this acts as an absorbing excuse me, vertex. I'm actually sick and have a cough and runny nose. It's not COVID. I was tested and it's negative, and I'm actually fully vaccinated already. So even more reason why it's negative. So yeah, it's just like an ordinary cold. So if I cough and blow my nose, that's why. All right. So what we're going to do is we're going to do a random walk on this graph where vertex 2 is marked. So it's an absorbing vertex, and we're going to work out what happens. So again, we start off in our initial state where we start at the vertex at random. So what that means is that initially, each vertex has probability 1/4 of so the walker has a probability of 1/4 of being at each vertex. So as a probability distribution, the graph or the state of the random walk excuse me, looks like this. So we have probability 1/4 of starting at vertex 1, probability 1/4 of starting at vertex 2, probability 1/4 of starting at vertex 3, and probability 1/4 of starting at vertex 4. Because again, we start at a random vertex. And now what we're going to do is we're going to take steps of the random walk. So let's take a step of the random walk. Okay, so let's see what happens at each vertex. So at vertex 1, there's currently a probability of 1/4. And what's going to happen is 1/3 of that is going to jump to 4, 1/3 of that is going to jump to 2, and 1/3 of that is going to jump to 3. So 1/3 of 1/4 is 1/12. So if I draw this out, basically we get a probability of 1/12 that jumps from vertex 1 to 4, because again, that's 1/3 of 1/4. We get 1/12 that jumps that way and 1/12 that jumps that way. Similarly, at vertex 4, it's also probability 1/12 jumps to 1, 1/12 jumps to 2, and probability of 1/12 jumps to 3. And same thing at 3, right? Because you have 1/3 going left, up, and to the right. And so 1/3 of 1/4 is 1/12. So you have 1/12, 1/12, and 1/12. And then at vertex 2, this probability of 1/4 just stays there because it just has a self loop like that. So what do we get when we put all these together? Well, if you look at vertex 2, it has a probability of 1/4, and we're adding to it 1/12 and 1/12 and another 12. Oh, that should be 1/12. There you go. So we have 1/4 plus 1/12 3 times. So 1/4 plus 3/12, that's another 1/4. So I have 1/4 plus 1/4, which is 1/2. So now the probability of the random walker being at the marked vertex is 1/2. And the probability of being at one of these other vertices. So basically we have 1/12 and 1/12 that swaps, 1/12 and 1/12 that swaps. So we have 1/12 twice at vertex 1, which is 2/12, which is 6. So we have probability of 6 that the walker is at vertex 1, a probability of 6 at the walkers at vertex 4, and a probability of 6 at the walkers at vertex 3. And indeed, if we add all these probabilities, we get 1, as we should. So it looks like we're doing things right. So what we see here is that after a step of the random walk, we're now more likely to have found the marked vertex, vertex 2. Because initially, when we started off with a random guess, we had a probability of 1/4 of being at the marked vertex. And now after one step of the random walk, we now have a probability of 1/2 of being at the marked vertex. And so we could keep going with this process. So if you take another step of the random walk, now 1/3 of 6 would jump in each direction. So that would be an 18th in each direction, and 18th and 18th in all of these directions. And so the the probability at vertex 2 would be a half plus an 18th 3 times, and so forth. And so let me just sketch what you would get and make a new page. So take a second step, and I'll leave this as an exercise for you to break up like this. But the end result is the following. Now you can see why I only picked 4 vertices instead of like 10 vertices. It takes a while to draw. So again, the probability would be half plus an 18th 3 times. So 3, 8. So I think we get 2/3. And then the probability at vertex 1 is a 9th, a 9th, and a 9th at each of these. And so that, I believe, adds up to 1. So the total probability is 1. So now we see here that after 2 steps of the random walk, that the probability of the random walk being at the marked vertex is now 2/3. So it's gone up yet again. And I'll just tell you, if you take a third step, and again, this is an exercise, the probabilities you would get would be the following. You get probability of 7/9, which is still higher at finding the marked vertex, 2/27 of being at each of the unmarked vertices. And so we see that the probability is increasing. There's a question a few minutes ago that I missed because I didn't scroll down in the question box. Can we assign different probabilities to jump to different nodes? Yes, you can. So in this case, we are doing a walk on an unweighted graph, meaning that if you're at vertex 1, then with equal probability, a third, you would jump to each of its adjacent vertices. But if you do a random walk on a weighted graph, then you would change those relative probabilities. And so, yes, you can. And there's been some work on that as well. Thank you for the question. All right, so let me go ahead and plot how the probability at the marked vertex is changing with the number of steps. So the probability at the marked vertex, this is basically our success probability. So the probability that we'll successfully find the marked vertex. I'll call this success probability. All right, so let's say we have a quarter, a half, 3/4, and 1. Oops, that shouldn't be there. So if we have 0 steps, remember that our initial state is that we equally guess all the vertices. So you start a random vertex, so the probability is a quarter. So it would start here. After 1 step, the probability of finding the marked vertex jumped from a quarter to a half, and then 2/3, and then 7/9. So we go to a half, 2/3, 7/9, something like that. And so basically what you see is that this is going to increase and it's going to asymptote towards 1. So as we take more steps, the probability that we find the marked vertex is getting greater and greater and greater. And so you can actually work out the math, and it's in that archive paper that I referenced earlier that's called Unstructured Search by Random and Quantum Walk. You can actually find what this function is, and you can find how many steps it takes to reach some probability, some constant probability, for example. And so I'm going to tell you what the answer is. So again, doing some math, you find that you reach a success probability of 1 minus epsilon, so just short of 1, after this many number of steps. And this is for large n. So I should say that for large n. So this is asymptotically, although the paper includes not asymptotically for like any value of n as well. But it's more complicated and isn't worth writing down for this talk. So for large n, this success probability reaches a height of 1 minus epsilon. after n times the natural log of 1 minus epsilon steps. So this is the amount of time it takes to reach a probability of 1 minus epsilon. And so basically, if you let epsilon be some constant, it can be 1%, 0.01 if you want, so that the success probability reaches 99%, which is a constant, then that occurs after order n steps, because the natural log of 1 over 0.01 is a constant. So basically, the overall runtime is order n. And again, if you're familiar with Grover's algorithm, you know that the classical algorithm searches in order n, and the Grover's algorithm searches in order the square root of n. So the quantum walk is going to search in order the square root of n. I guess this is letter C in our outline. So the asymptotic result. Let's see, any questions? Doesn't look like it. All right. Excuse me. Oh, it looks like there's a question in the chat as opposed to the Q&A, which is, what happens if the marked vertex is not an absorbing vertex? Well, so in a classical random walk, the marked vertex is an absorbing vertex, because if you're the marked vertex and if you jump to the marked vertex, you would just stay there, you wouldn't leave. So yeah, so the marked vertex is an absorbing vertex for a classical random walk. That's not going to be true for the quantum walk, because, well, I'll get to it, I guess, now in our quantum walk section. So let's see how discrete time quantum walk would solve this same unstructured search problem. Oh, scroll down, let's clear the question. What happens if there's more than one solution vertex? Great question. So if there's more than one solution vertex, then let's say vertices 2 and 3 were marked, then vertex 3 would now be an absorbing vertex as well. So this would also have a self loop, because once you jump to a marked vertex, you would stay there because you found a solution. And so you could have multiple vertices that are marked vertices that are absorbing vertices. And so what would happen with the runtime is, let's say there are k marked vertices, then the runtime would be order n over k. So that is what would happen. All right. And it's actually very easy to analyze on the complete graph, because the symmetry of this, because everything's connected to everything else. If you had a more complicated graph, something like this, then it makes a difference which pair of vertices are marked if you have 2 marked vertices. And so in general, how much time it takes could be different depending on which 2 vertices are marked. Or even if you just have 1 marked vertex, you might imagine that the time would be different depending on which vertex is marked if you have something more complicated like this. And so that's actually still a big open question in the field, which is how long does it take to search general graphs that could be really complicated, especially if there's multiple marked vertices. And it just increases the number of options. Good question. Excuse me. Okay, doesn't look like there's any more questions for now, so let's keep going. So one of the big things that makes a quantum walk different is that there's an additional space involved called a coin space. So I want to talk about that here. Oh, maybe I should mention that I'll make these notes available as well. So you don't necessarily have to take notes in real time. So what I mean by this is, let me draw what we had before. So when we had 4 vertices, 1, 2, 3, 4. So here's a complete graph with 4 vertices. And we assigned a probability to each vertex. So we had the probability of being at vertex 1, vertex 2, versus vertex 3, and vertex 4. We have 4 probabilities. And you might, so in order to make this quantum, what you might try to do is replace these 4 probabilities with 4 quantum amplitudes so that the system is a superposition over these 4 vertices. And then so you have an amplitude at each vertex. And then to get the probability, you take the norm square of the amplitude. And so write that down. So instead of 4 probabilities, or in general, n probabilities if the graph has n vertices, can we replace it with 4 amplitudes? And it's a very reasonable thing to try. And indeed, people try this, and it turns out that no, you don't want to do this. There was a question about the first diagram, this kind of random looking network I drew. This, it says, what happens if not all the nodes are, so what happens if, oh, so basically in the complete graph, these are all interconnected. What happens here? So, I mean, in general, we don't know what the runtime is. So, yeah. I guess there's a reason why this is still a very active research area. So, yeah. So your question is getting right to the question of like what happens on other graphs that are not so nice, like the complete graph. And in general, it's hard to know, and it also depends on what type of quantum walk. We know more about certain types of quantum walks than with others. Okay, so back to this. So I was raising the idea that we just replace these 4 probabilities with 4 amplitudes so that the system is a superposition over these 4 vertices. And it turns out that you don't want to do this. So can we do this? Well, no. I guess you could, but you don't want to. And that's because David Meyer in 1996 showed that if you do this, then the evolution of this type of quantum walk is actually trivial, that you don't get something interesting. So Meyer showed this evolution is trivial, assuming some really reasonable things that you would want the quantum walk to do, like properties that you would want the quantum walk to have. So if you want the quantum walk to have some reasonable properties, then the evolution ends up being trivial. And so what he came up with in order to make it non-trivial was to include an additional space that you can interpret either as like the spin of the particle that's randomly walking around, or typically now we call it some type of coin space. The idea is like you flip a coin, and then that tells you which way to walk is the idea. So to make it non-trivial, we're going to add what we call a coin that determines which way the walker points. And I'll draw a picture to explain what I mean by that. So what I mean is that instead of just a probability or an amplitude, I should say, because it's quantum now, an amplitude at vertex 1, we're going to have some amplitude of being at vertex 1 and pointing to vertex 2. So we'll call this amplitude, I don't know, it's called alpha 1, 2. So the amplitude of being at vertex 1 and pointing to vertex 2. We have some amplitude of being at vertex 1 and pointing at vertex 3, and some amplitude of being at vertex 1 and pointing to vertex 4. At vertex 2, again, you have some amplitude of being at vertex 2 and pointing to vertex 1, some amplitude of being at 2 and pointing to 3, and some amplitude of being at vertex 2 and pointing to 4. And same thing here, amplitude of 3 pointing to 1, pointing to 2, and pointing to 4. And at vertex 4, you have some amplitude of pointing to vertex 1, some amplitude of pointing to vertex 2, and some amplitude of pointing to vertex 3. So instead of 4 amplitudes, we actually have, 4 times 3? We have 12 amplitudes. And so, so instead of 4 numbers, we have 12 numbers. And so this is one of the big things that makes a quantum walk different. And it's a quantum thing. So basically the state of the quantum walk is a superposition over these 12 possibilities. All right, so with this in mind, let's go ahead and work through what the algorithm is. see any questions. I don't see any. All right. So just like with the classical random walk, we're going to start in a uniform state initially. So before we had a probability of a quarter at each of the vertices. So now because we have 12 amplitudes, they're going to all start off with the same value. All right, so basically, each of these amplitudes is going to start off with a value of 1 over root 12. Because remember, this is quantum mechanics, so if you want to convert this to a probability, you would take the norm square of it. So the probability of finding that the walker is at vertex 1 and pointing to vertex 2 would be the norm square of 1 over root 12, which is 1/12. So basically, this is a uniform distribution. And in fact, if you were to measure the position of the particle, which you wouldn't want to do, I mean, you want to let it evolve quantumly. You don't want to just measure it from the start. But just to keep track of the numbers, what's going on, if you were to measure the position of the quantum walk, you would find that it's at vertex 1 with probability 1/12 plus 1/12 plus 1/12. Because again, the probability of finding it at 1 pointing to 2 is going to be 1/12 because you take the norm square. The probability of it being at 1 pointing to 3 is a 12th, and the probability of it being at 1 pointing to 4 is a 12th. So the probability of it being at vertex 1 is going to be the sum of those. So a 12th plus a 12th plus a 12th, 3/12, which is a quarter. And you can see the same thing for all of these. So if you were to measure the particle, you would find that it's at a probability of a quarter. That with probability a quarter, you'd find it at each of the vertices. So this is a uniform distribution over all the vertices, just like we had before. But we've made it quantum, so we have amplitudes, and we have these this coin space or the directions that the walker can point. All right. Oh, it looks like there's a question. We scroll down. What happens at the marked vertex, which is absorbing in the quantum walk case? So we're actually going to talk about that next. So that is a great question, Annie. Thank you for that. I should mark these. Answer live. Answer live. Answer live. Okay. So let's go ahead and work through the algorithm now. So remember, the first thing you do with the algorithm is you ask, like, you ask, am I at a marked vertex? So you're querying the oracle. So just like before, let's say vertex 2 is marked. And I mentioned earlier that in the quantum case, vertex 2 is not an absorbing vertex. And the reason for that is, again, in the classical case, if you have an absorbing vertex, that means probability jumps there, but then it never leaves. And the issue with that is that that is not reversible, so it's not unitary. So you actually can't have an absorbing vertex in this sense quantumly, because you have to evolve using reversible operators. And so it's not an absorbing vertex. So what actually happens when you convert an absorbing vertex to a quantum walk, and again, I'm skipping all the math and the linear algebra and stuff, is that when you query the oracle, what happens is that the amplitudes at vertex 2 end up getting a minus sign. So this becomes negative 1 over root 12, this becomes negative 1 over root 12, and this becomes negative 1 over root 12. So let's actually put that down here. So let me just copy and paste it faster. So, oh, and then write down a sentence about that. So so vertex 2 is marked, and absorbing vertex isn't reversible or unitary. So all quantum gates have to be unitary. So instead, the oracle negates the sign or flips the sign of at the marked vertex. Instead, the oracle flips the amplitudes at the marked vertex. And if you're familiar with Grover's algorithm, oops, I wrote G because I was saying Grover. If you're familiar with Grover's algorithm, this is the same thing that the Oracle does in Grover's algorithm. It takes your marked state and it makes it negative. So, oh, it looks like there's a problem in the chat. I was looking at the question and answer, the Q&A. How about treating each vertex as a two-faced coin so that the outcome of problem? So each vertex in this drawing has 3 neighbors. So you'd want your coin to be a 3-dimensional coin, not a 2-dimensional coin. A 2-dimensional coin would be something like a 1-dimensional walk on a line where you can jump to the left or to the right, something like that. And so, so basically, you need enough directions for the number of neighbors that you have. Oh, it looks like there's something Q&A. Oh, now it's in the Q&A. Okay, I just answered it. Okay, thank you for moving that question there. All right, so what happens is after we apply the oracle, these amplitudes become negative. Maybe I'll color it in a different color just so it stands out. So those become negative, and then everything else stays the same. So again, just like in Grover's algorithm, the oracle flips the sign of the marked state. So in this case, it's at the marked vertex. Now what we'll do is we'll take a step of a quantum walk. So a step of the quantum walk has 2 parts. The first part is a coin flip that shuffles the coin directions. And then you actually hop, or what we could say shift, and a shift or a hop. So let me explain how each of these work. So let's start with the coin flip. What it does is it inverts, at each vertex, let's say, we invert the amplitudes about their average. So this isn't going to be very interesting for the first step. When we do the second step, it'll be much more interesting. So what I mean by this is let's look at vertex 1. It has 3 amplitudes, 1 over root 12, 1 over root 12, 1 over root 12. The average of those 3 amplitudes is just 1 over root 12 because they're all the same. So if you invert 1 over root 12 about the average of 1 over root 12, nothing happens. And similarly, this one and this one. So nothing happens to these. And that's the same for vertex 4 and vertex 3 as well. And vertex 2 is the same idea, right? Its 3 amplitudes are negative 1 over root 12, negative 1 over root 12, negative 1 over root 12. So their average is negative 1 over root 12. So if you invert these about that average, nothing happens. So in this first step, nothing actually happens. When we do a second step, it will be far more interesting. So in this case, nothing happens. So I'll just copy that. And let's keep going. And finally, we're going to do a shift or a hop. And what we do is what's called the flip-flop shift, meaning that if you're at vertex 1 pointing to vertex 2 with this amplitude, 1 over root 12, what happens is that you hop and then you turn around so that you're pointing back to vertex 1. So basically what happens is these 2 amplitudes will swap. Similarly, these 2 amplitudes will swap, but since they're the same value, basically nothing happens. This pair will swap, this pair will swap, this pair will swap, and this pair will swap. So basically the amplitudes will jump and then turn around. So what we end up getting as a result of that is the following. And I'll copy and paste. Oh, new page. So what happens then is that this negative sign ends up moving over here. This negative sign ends up moving here, 4 pointing to 2. This one ends up moving over there like that. So now we do have a little bit of a change. And so this is one step in total. So basically we query the oracle and then we've taken one step of the quantum walk, which is a coin and shift. Now let's do it a second time and see that we get something more interesting, because at this point, actually, the probability is still the same as what we started off with. So if we were to measure the position of the quantum walk right now, what we get is that the probability of finding the walker at 1 pointing to 2 is going to be 1/12 because it's the norm square of this. The probability of 1 pointing to 3 is also a 12th, and 1 to 4 is a 12th. So the probability of the walker being at vertex 1 is going to be 3 times a 12th, which is a quarter. And you can see it's the same thing for all of them. So at least with the quantum walk, it doesn't actually change your probability distribution in the first step. We actually need to do a second step. There's a question of what we make one vertex that gains and the other absorb. Again, you don't have absorbing vertices in the quantum walk because it's not unitary. And so I'm not exactly sure. There might be something more subtle that you're thinking of that I'm not reading from the question. So yeah, so if you have more that you'd like to add to that, feel free to ask again. Okay, let's do a second step. So what we're going to do is we're going to query the oracle. And again, what that does is that it flips the signs at the marked vertex. So here's the mark. If the marked vertex is 2, then all of these amplitudes will become negative. So let's go ahead and copy and paste. And so these become negative. Now let's apply the coin flip. Oh, this coin flip that inverts the amplitudes about the average, that's the same as the Grover coin. If you're familiar with Grover's algorithm that inverts about the mean, it's the same idea, except we do it at each vertex. Okay, so now the coin flip is more interesting. So let's look at vertex 1. So its amplitudes are -1 over root 12, 1 over root 12, and 1 over root 12. So its average, so let's see, this is vertex 1. So the average of those, which I'll call mu, is literally the average or the mean. So if I add up all of those amplitudes and I divide by 3, the average is, let's see, those cancel. So it's 1 over 3 root 12. So that's the average of these 3 amplitudes. And I want to invert each one about that average. So let's start with this amplitude, -1 over root 12. Let's invert this about this average. So let me draw a number line to kind of geometrically explain it. So let's say the average is here, 1 over 3 root 12. And this amplitude is -1 over root 12. So it's going to be somewhere over here. What we mean by inverting is we want to take this amplitude and we want to invert it to the other side of this. So that's the same distance away from the average. So this distance here, if you subtract that, this is 4 over 3 root 12. So we want to end up a distance of 4 over 3 root 12 to the right of the average now. So if we add 4 over 3 root 12 to this, we get 5 over 3 root 12. So this amplitude becomes 5 over 3 root 12. Let's look at these amplitudes that are positive 1 over root 12. So again, the average of those 3 amplitude is 1 over 3 root 12. And the amplitude before our inversion is positive 1 over root 12. So we want to invert to over there. So this distance here, I worked it out, is 2 over 3 root 12. So we want to end up 2 over 3 root 12 to the left. So if you subtract 2 over 3 root 12 from the average, this is 1 over 3 root 12. And so this amplitude becomes 1 over 3 root 12, so negative 1 over 3 root 12, and this amplitude becomes negative 1 over 3 root 12, and so forth. So let me go ahead and draw this out. We should be able to finish in 5 minutes and then leave a few minutes for questions. There's been a lot of questions along the way, so hopefully the remaining questions won't take too long. All right, so this amplitude here, we worked out becomes 5 over 3 root 12. These two amplitudes each become -1 over 3 root 12, -1 over 3 root 12. And it's going to be similar here, -1 over 3 root 12, This is 5 over 3 root 12 minus 1 over 3 root 12 minus 1 over 3 root 12 minus 1 over 3 root 12, and this is positive 5 over 3 root 12. And finally, to invert about the average here, so all of these amplitudes are minus 1 over root 12, so their average is minus 1 over root 12. So when we invert about the average, nothing happens. So these are minus 1 over root 12, minus 1 over root 12, minus 1 over root 12. Excuse me. So that's what happens when you do the coin flip. And finally, to finish off the second step, we have the shift or the flip-flop shift. So if we apply the shift, what happens is that the particle walks and turns around. So these two amplitudes will swap places. And similarly, every pair of amplitudes that are pointing to each other will just swap around. And so I guess I'll draw it. All right. All right, so if these two swap, this becomes minus 1 over root 12. This one becomes 5 over 3 root 12. All of these become 5 over 3 root 12, 5 over 3 root 12, minus 1 over root 12, minus 1 over root 12, and these are minus 1 over 3 root 12, minus 1 over 3 root 12, and so forth. Maybe I won't fill in the rest just for time's sake. These are all minus 1 over 3 root 12. Okay, so this is after the second step now. Let's see what the probability would be now if we were to measure the position of the particle or the position of the walker. So if we were to measure now, the probability at vertex 1 would be the norm square of this plus the norm square of this plus the norm square of that. And if you do that, you get a probability of the following: 11 over 108, 11 over 108, 11 over 108. And the probability at the marker vertex is 25 over 36, which is much bigger than a quarter. So you see now that the probability has gone up. And so if you plot the probability versus time, just like before, it's at 0 steps, it's a quarter. After 1 step, it's still a quarter. After 2 steps, it's now 25 over 36. So it jumps way up here. And actually, if you keep doing this, you'll find that it like oscillates funny. And so let me actually show you what this looks like. If you work it out carefully, it actually looks like this. So you see that it starts at a quarter, and it jumps to that 25 over 36. It goes down, goes back up, and it oscillates like crazy. And so, this is a little wild to see. Let's see what happens for large n. So this is n equals 4. Let's say we have n equals 100. If n equals 100, we end up getting this. And you can see it's kind of smoothed out now a little bit. The wiggles aren't as dramatic. And let's say we have n is equal to 1,000. You end up getting this. So you see again that the wiggles have calmed down quite a bit. I need to put this on another page. For n equals 1,000. All right. So basically what happens is that the success probability reaches a value of 1/2. And so you can do all the math for this. So for large n, the probability reaches 1/2. And the number of steps it takes is pi over 2 times the square root of n steps. So we reach a constant success probability at this time. So the overall runtime is order the square root of n, just like Grover's algorithm. And so we get a quadratic speed up using a quantum walk. And so there are tons of reviews and stuff like that on quantum walks that you can just Google. There's tons of other algorithmic applications of quantum walks, again, which will be in the reviews. Quantum walks are also universal for quantum computing, so you can convert any quantum circuit to a quantum walk and vice versa. And so there's a lot of things in this field. And rather than going to everything, I wanted to just give you one specific example that hopefully you were able to follow.